Going back to the Navier-Stokes, this is what we did when we cut off last. And so essentially we derived, we physically motivated the appearance of the viscous term in addition to the other terms of the momentum equation that we were already familiar with. So let's do it a little more formally, since the Navier-Stokes equation is so important. It's a momentum equation, but since it's so central to all of fluids, it's important to look at it from a couple of different points of view. This is one point of view that we've already come across, in fact. Okay. Now, remember, we can have normal as well as tangential stresses on each face in a fluid volume element. We've looked at this earlier as well, and it's just this. I'm going to draw this a little better, like this. So, on a given face, you can have normal stresses. In other words, you can have a force per unit area in this direction as well as along the face, right? And these would represent, these kinds of normal forces would represent pressure, and these kinds of tangential stresses, which a normal stress would be like this, and tangential stresses would be like this or like that, yeah, as we've said several times before. And this volume is of course an imaginary volume. It's not an actual physical thing. So instead of, so we said when we were talking about inviscid fluids, remember we said we were specializing to a situation where the pressure tensor was like this. In other words, if you had the pressure tensor was like essentially a matrix, you only had the diagonal elements. You only had the diagonal elements, and the off diagonal elements were all 0. Okay, so you only had this, this, and this. The rest of them were all 0, right? Which is what this is saying. Unless I is equal to j, you have zeros. When I is equal to j, then you have p, p, p. This is okay for inviscid fluids, but in general, that's not always true. You have a pressure tensor, so you have the diagonal elements as they were before, plus on top of that you have the shear stresses. You have the sigma ij's, right? So let's now see how to go ahead. So yeah, as always, Pij is a force in the ith direction, I can be x, y, or z, on the face whose outward normal is in the jth direction. Again, j can be x, y, or z. If it so happens that j is equal to I, you have pxx or pyy or pzz. If not, you have the shear stresses. So when I is equal to j, you get the diagonal elements of the pressure tensor. If not, you have the off diagonal elements. Right. So we've said this before, and what we're now saying is no different from that. So P is this quantity, this small p that we wrote down, this one is still the thermodynamic pressure, but there are some caveats. So the question now is, what would sigma ij look like? Okay, what would the shear stresses look like? We've written it down formally, but what would it look like? Again, we go back to our definition of Newtonian fluids. Recall, Newtonian fluids are ones where the shear stress, the force per unit area, which is this tau, is related to the strain, which is du dy, via a proportionality constant called mu. Now this mu need not be the same for xy as it is for yz. It need not be the same, but as such, just to motivate the idea, it's good to go back to this kind of a one-dimensional treatment, right? So therefore, clearly the sigma ij's, which were these guys, these off diagonal terms, they will clearly involve velocity derivatives like dui dxj, where I and j can be any of x, y, and z. So for instance, this could be dux dy, right, duy dz, and so on and so forth. I and j can take on any of the x, y, z numbers, right. So, but the thing is the sigma ij will involve velocity derivatives of this kind, cross derivatives. If you have an x here, it would be a y here. If you have a y here, there could be an x here. There would be cross derivatives, right. So, this is a general way of writing it. So, a dui, you can immediately see that this is true, just algebra, this is true. There is a reason we write it this way. That is one of the most general ways of writing down dui dxj. Now, it turns out that the second term, this guy, represents rigid body rotation of this kind, where omega is a constant. And you can show this. It is not hard to show that this really is this kind. So, whenever you have rigid body rotation, the rotation is rigid. There is no question of velocity streamlines looking like this. There is no question of that. These are arrows. Yeah, there is no question of velocity streamlines decreasing. I mean, the length of the velocity vector is decreasing. It is rigid body rotation. So, this does not involve shear stresses. Now, if we insist on Newtonian fluids, the most general second rank tensor, which is what this is, second rank because it has two indices, I and j, involving velocity gradients, is of this form. I do not want something that looks like this. I only want something that has a plus sign. Okay, you can see that by way of dimensions, the dimensions of this divergence and this are the same. Okay, except there is a delta ij here and there is no delta ij here. That is the only difference. And I stick an a here and a b there. We will see what we will do with these for the time being. Let us just take this and proceed. And recall that this was my basic definition of capital Pij. I had the diagonal terms here and the off diagonal terms here. Right. So, if we take P, this small p, this guy, to be the scalar pressure, the scalar thermodynamic pressure, it contains a trace of Pij. In other words, I add up the diagonal terms of Pij and that should add up to small p, the thermodynamic pressure, right. So, in other words, the small p is 1/3 of Pii, sum of all the diagonal elements. And in which case, if this contains a trace, this had better be traceless. This had better, I mean, in some ways this is obvious. I mean, these are the off diagonal elements and these are the diagonal elements. So this, if you construct a matrix with only the shear terms, it had better not have any diagonal elements at all. It had better be traceless. That's another way of looking at it. Okay, and the only way this can happen is if the relation between this A and B that we wrote down here, this A and B, is of the form B equals minus 2/3 A. That's the only way this can happen. That's the only way, this and this statement can simultaneously be true. In which case, the sigma ij looks like this. And here I am specializing to the slightly simpler situation where the coefficient of viscosity is the same for all combinations of I and j. Okay? So, which is why I can write this as a scalar term. I have taken it outside of the brackets. And so, this is the final, in some sense, the most general form of the shear stress tensor. Okay? I now make a distinction between the shear stresses and the normal stresses. The normal stresses are this and the shear stresses are this. Okay. So, putting it all together, this is how it looks. So, these are the body forces. Right. This is the pressure gradient. And what are these? These are shear stresses. shear, I put the stresses under quotes because this is really the force arising from shear stresses. So, it is this as such, this is because of shear stresses. So, this is a force, that is a force, there is also a force, okay, that is arising from shear stresses. Okay. And this obviously has to do with viscosity. The coefficient of viscosity is this mu, right. So, this is the Navier-Stokes equation in its so if mu is isotropic, it can be considered to be a scalar, and we get, if that is the case, instead of this pesky notation, if you wanted to write it down in regular in terms of gradients or divergences, this is how it would look. Yeah, and recall, so this looks very similar to what we had written down a few slides earlier. The shear term looked or the viscosity term looked just like this, and this was missing. Okay, this is what is called bulk viscosity. This is arising due to bulk viscosity, and this term will, you can write this down if only if you consider this way of doing things, slightly more formal way. And for incompressible flows, for which the divergence of u vanishes, okay, incompressible flows, divergence, remember, that is what an incompressible flow looks like. So, you recover this, which is what we had written down from somewhat more intuitive considerations, and you recall that without this, this looks just like, this is essentially the Euler equation, and the straight du dt, this is of course a Lagrangian way of writing it, and if you wanted to write it down in the lab frame, the Eulerian frame, you would have the partial derivatives, which we know how to do. You remember, is the same as right. So, if you do not like this way of writing things, you can always write it this way, same thing, right. So, and finally, let us talk a little bit about energy conservation. We have already seen energy conservation in the guise of the Bernoulli constant, but now let us include viscosity. Okay. So, recall, this we have already seen, Pij, this we have already seen, and the viscous stress tensor is this. We just wrote this down, and the Navier-Stokes equation can equivalently be written as this. It is really the same as what we wrote down here. It is really the same as this. Okay. Having talked about the mass conservation equation and the momentum conservation equation, mass conservation was simple enough. We did not have to worry about viscosity at all. In momentum conservation, we had to pay a fair amount of attention to viscosity. For an inviscid fluid, we talked about the momentum conservation in the absence of viscosity, which was called the Euler equation. And for a viscous fluid, we had to include viscous stresses, and the momentum conservation equation in that case is generally called the Navier-Stokes equation. So, we discussed that in some detail in a couple of different guises, and now we will do a little bit of talking about the energy equation. Just want to mention that we have really already seen energy conservation in the guise of the Bernoulli constant. But if you recall the Bernoulli constant, when we talked about the Bernoulli constant, we were talking about inviscid liquids where viscosity was not included, and we were also talking about incompressible flows, which we will in what we're going to be discussing right now, we will still be talking about incompressible flows. Viscosity, compressibility is not included. That introduces additional complications, and we won't bother about that for the time being. Okay, but let's see what viscosity does. Okay, let's see what viscosity does to energy conservation, and we will concentrate only on that part. since we've just gotten off talking about viscosity in some detail in the context of the momentum conservation equation, let's see what viscosity does by way of energy conservation. And just to jump to the bottom line, what viscosity will do. Viscosity, as we have already said earlier, viscosity is kind of a frictional kind of force. Yeah, it dissipates energy. So we will anticipate that result, and we will see that the kinetic energy, rate of change of kinetic energy, rate of change of kinetic energy of a fluid parcel, it will turn out to be some kind of it will turn out to be an expression like mu This is what viscosity does for you, where, as you know, mu is the coefficient of dynamic viscosity. So this will be our main result after this discussion. Okay, so let's see how it comes about. We will follow Landau and Lifshitz here. Yeah. So now recall the pressure tensor. We split it up into the diagonal part and the off diagonal parts, right? And this includes the off diagonal parts, and this includes the regular thermodynamic pressure. And for incompressible fluids, the off diagonal part was just this. Yeah, this is what we did in the previous slides. And the Navier-Stokes equation, which we wrote down, can equivalently be written as this. Yeah. So what we've done is we've divided by the density throughout, and it's really the same thing. Wherever you see a repeated index, it implies a summation. In other words, this would be, say, u1, and I is constant, so du1 dx1 plus u2 du1 dx2 plus so on and so forth, where x1 could be x, x2 could be y, and so on and so forth. So wherever you see an index which is repeated, here you see the k is repeated, it implies a summation. Okay, so repeated indices summation is implied. Okay, so that's the only, here there's really a sigma here, and here too there's really a sigma, because you see you have repeated indices here, the k is repeated. It's just not written for the sake of brevity. Okay, right. It's just the same Navier-Stokes equation that you've seen earlier, no different, and yeah, so just keep the repeated summation in mind, and let's proceed. Now we're interested in knowing how the kinetic energy, half rho u squared, energy density to be precise, so half mv squared will be the kinetic energy, and half rho u squared is the energy per unit volume. Okay, how the kinetic energy of a parcel of fluid evolves over time. What viscosity does to it in particular. Okay, because we've already seen the energy equation for an inviscid parcel of fluid. That's essentially the Bernoulli constant, right? Although it's strictly speaking valid only over a streamline. Okay, so in other words, what we want to evaluate is this quantity, d over dt in the lab frame, as seen by an Eulerian observer, of this quantity half rho u squared. Another way of writing this is this. Okay, this is easy enough to see. You see, d over dt of u squared is 2 u du dt, and that's essentially what this is. Okay, and the 2 and the half cancel, and that's all this is. Okay, and since there is a repeated index, it implies a summation. So let me write this down. Summation implied. Okay, the summation is implied. Now, using the form of Navier-Stokes, which is this, which we wrote down in the previous slide, So I'm going to be obviously substituting for this, right? This is just this whole thing, right? So it gets a little messy, so let's bear with me. So you get, and now I switch back to, well, a mixture of vector and tensor notations. I keep this as it is, okay, and the rest of them, these guys, I write them down in usual vector notation. There's a reason for doing it this way. It's about convenience, and it'll become evident as we go along, right? It's a bit of a mixed notation. Yeah, and this again can be simplified as this. So turns out that right. So this can be split up into two terms, like so. Yeah, and these guys can be written as this. Okay, you recognize this immediately. It looks very much like the Bernoulli constant, right? It's and then there's a divergence of u dot sigma, where sigma is, you know, the viscous stress tensor, and again, you know, since there's a sigma ik dui dk, there's a repetition of k, so there's a summation implied. Okay, just like there was a summation implied here, there's a summation implied here as well. Okay, so again, all of this is simply this the time derivative of the evolution, well, the time derivative of the kinetic energy density of a fluid parcel. In other words, how the kinetic energy density of a fluid parcel evolves and how it's related, specifically how it's related to viscosity. Okay, right. So now we specialize to incompressible fluids. Divergence of u is 0. And that simplifies this term a little bit, and we get the same thing. It's a little simplified, and it becomes like this. Okay. Now we're going to do something interesting, very important, and we integrate over a macroscopic volume and bounding area. What I mean is that we integrate over the entire body of the fluid. The fluid is essentially unbounded, okay, and so the bounding area is essentially taken all the way up out to infinity, and I'm going to be using Gauss's divergence theorem here. We will see. Yeah, so the integration is over the volume, yeah, and here since this is the divergence, it becomes an integration over the surface area, except now the surface area is at infinity, and this is important. Okay, so in going from here to here, this is also, you take a volume integral of this term and you use Gauss's divergence theorem to turn it into a surface integral. Here, this we keep as a volume integral, and we're going to do something clever with this, and that's why, and that's also why I emphasize the fact that in this surface integral, I'm at the surface, I'm integrating over the entire fluid, and the bounding surface, I take it to be at infinity. And as a consequence of that, I am allowed to throw this entire thing away. This entire thing vanishes. Why is that? Notice that we have a u here, and for any well-behaved flow, you assume that the velocity of the flow vanishes at infinity. So you're integrating only over the surface, which is at infinity, and the u essentially vanishes, so that allows me to throw this entire thing away, so that I'm only left with this term and this term. That's pretty nifty, and that simplifies my life greatly. Therefore, what I finally have is the E dot kinetic, yeah. This is kinetic energy, this is kinetic energy density, isn't it? And the E dot kinetic, in other words, the time derivative of the kinetic energy density, is equal to this quantity, you know, integrated over volume, which is this, simply you know, substituting for this, right? And substituting for sigma ik, well, here I have not yet substituted, I'm simply writing this as in the same spirit that we did earlier, and substituting for sigma ik, we know that this is the definition. In other words, this is only for Newtonian fluids, mind you. This is the definition, so to speak, of a Newtonian fluid. Okay, I get. So this quantity gets squared because inside the sigma ik I have another thing, inside the sigma ik I have another thing that this bracket thing that appears again here in sigma ik, so it gets squared, right? And this is my final result. So this looks very much like, if the flow were just one dimensional, this looks very much like mu times du dx quantity squared. Okay, so therefore the time rate of change, this is the final result. This is in some sense how the kinetic energy density of a fluid parcel is dissipated due to viscosity. And we understand this, this agrees with our intuitive understanding of viscosity as a frictional kind of force. And so, if you're considering only inviscid fluids, then there's no dissipation at all. The introduction of viscosity results in dissipation. So the bottom line of all of this is essentially this expresses viscous dissipation, of kinetic energy. This whole thing. Okay, so there you have it. This is how the energy equation is modified in the presence of viscosity. And we're done with this section of the course, and we'll proceed to other topics from now on.